Hello, young buckies and buckets. On our experiment, we'll talk about magnetic field lines and their direction. We'll talk about the right-hand rule, and later we'll explain the magnetic field on a solenoid. So first, the basic is the magnetic field and the direction of the magnetic field lines. This concept, we can explain it by using a magnet which has a north and a south pole. And if we place a compass needle on a position close to the magnetic field lines will always point from the north to the south pole, since the needle of a compass is always attracted from the north towards the south, and it's gonna form a closed loop, since due to the lack of single magnetic poles on a magnet. So that is why it has the shape of a loop. Okay, then in our experiment, since we're gonna use current, I'm gonna explain how so when we have a straight wire and we use that same concept, placing the compass needle close to the wire, it's gonna make the needle aligns tangentially, like on a circle, so around the wire, and that is why the magnetic field lines are always in a circular loop when we have the straight wire charged with a current. And the direction will be given by the direction that the needle has with the same concept applied in the magnet. Okay, so now we're gonna talk about the right hand rule and the magnetic field on a solenoid. Yeah.
Okay, now we're gonna go more in depth of our experiment. In our experiment, we don't have a straight wire, but we have a wire going under loops. This is what we can call a solenoid. So in the solenoid, we have this, and if we assume a current going in this direction through the wire, the direction of the magnetic field will be as shown by the blue lines. This will be the relation between the wire and the magnetic field if we set the loops with some space. But every time we make this space smaller and smaller, we're gonna get a more uniform and strong magnetic field towards the center of the solenoid. Okay, now we're gonna try to find the magnitude of the magnetic field. This we're gonna use Ampere's law. Okay, so in Ampere's law, we know that the integration of a closed loop of the magnetic field dot dl equals the mu naught, which will be the constant of permeability, times the I enclosed. So this is our situation. So we can have a rectangular section like this one. So this will be the current that is going towards us, and this will be the currents that are going into the board. This will be a side view of the solenoid. And this, of course, it will assume the same direction of the current going this way, right? When it goes from here, it goes back to here, the magnetic field will be in this direction, okay? So we have this rectangle. Well, we're gonna call these points A, B, C, and D, and we're gonna call this length L, okay? So we gotta find what is the total magnetic field enclosed here. So will be the integration, right, of B dl, right? So of course we're gonna have the integration from A to B of B dl plus the integration of B from B to C dl, and so on from C to D and D to A. This is just blah. So as we see, we can assume that the magnetic field just outside the solenoid and within the closed loops of the solenoid is almost negligible. Therefore, we're gonna only consider the integration from C to D, right? So we cancel all this, and we're gonna end up with, basically, we're gonna end up with the integration of closed loop from BPL from C to D, right? And this should equal mu naught times I enclosed, right? Therefore, we know that the magnitude will be BL cosine of theta, which theta is the angle between the L and the magnetic field. Therefore, as we see, L is going this way and the magnetic field is also going this way. Therefore, the angle between those two will be 0 and cosine of 0 is 1. That's why we end up with the magnitude will be only BL, right? So BL will equals mu naught times the I enclosed, right? But what is the I enclosed? The I enclosed will be I times the times of loops, right? How many times this goes to loops, right? Therefore, we can call this mu naught n, which will be the number of loops, times I, right? Now, we can finally solve for B, which is our magnetic field. And if we can call n, lowercase n, we can call n over L, which will be the number of loops per unit length, right? So we can solve now for B, and we're gonna end up with B equals mu naught, which is the constant of permeability of free space, and n, which is our number of loops per unit length, and the I that's going through the current. So what is the difference between all the theories explained and our experiment, the simple electric train, right? Is that in the theory, we are supplying an electric charge to that wire, which creates that electric current, right? But in this case, we don't have a battery supplying that wire, right? So how do we create that electric current? That electric current is created by the battery and the magnets that you'll see on our experiment, on the setup, and that completes a whole circuit which creates that current that therefore then will create a magnetic field which will push this setup. But how does it push it? It has to be set up in certain way so that the battery can move with the magnets, okay? So we have our battery, right? So we have our battery, and our battery has our minus and our plus, right? So here's our solenoid. We're gonna have to place the magnets. You can place 1, 2, as many as you can. That will actually make it move faster. And such that the north pole of the magnet, of the last magnet, has to point outside. So in this side, right? So we can place the magnets here, and the north has to be the last part. So both north poles of each magnet have to be in the opposite sides. Why is this? Because we need that the magnetic field implies a force such that will be pushing this side as also will be pulling this side. Therefore, we're gonna have the same direction of motion, right? Which is gonna make it move. Now, how do we determine which is the north pole of a magnet? It's easy. You can just place it on a table with nothing metal around, nothing magnetic around, and let it be free. And it will try to point towards the north pole of Earth.
You can also use the right-hand rule to determine the direction of the magnetic field inside of the wire. So let's suppose that this circle will be here. So by the right hand rule, we can say that the current is going this way towards the right. And when we use our thumb to point in that direction, our fingers are pointing inside of the board. So that means that our X means that magnetic field is going inside of the board. By using this equation, force equal the current times L cross D, where L is the direction of the length of the wire and B will be our magnetic field. We can say, by using a second version of the right hand rule, that in this case our L would be pointing with our fingers going towards the center where our magnetic field is in, and our force we're going inside. So if we see it like this, we have our L going towards the center of the magnetic field and the force will go inside.
Okay, so this is a basics experiment. We will only need 3 basic objects that you can find on any place. Not really hard to find. First of all, we need some copper wire. We use here 18 gauge copper wire. It has to be solid. So the core has to be solid in order to have an electric current that will flow through it. We need some neodymium magnets, which are very strong, and you can also find them on any place. They're not hard. And we need a couple of batteries. So the size of the battery depends on actually what will be the diameter of the coil that you're gonna make, the solenoid. So in our case, we use AAA batteries, which will fit perfectly with the size of the magnets through the hole. But you can also use maybe a bigger, a AA battery, and you have to make a little bit bigger space for that. So after you make this solenoid, which was just take the copper wire and wrap it around. Maybe we did it around this size of marker, which was a perfect size. So it depends on which type of battery you're using. Now, next thing is to set up the batteries with the magnets. Okay, so be careful because these magnets the neodymium magnets are very strong. So first of all, we have to find what the North Pole is, right? So we can place the magnet here, and you see it will always try to point north, right? So we know now that this side of the magnet, you can see there, is the north, right? So we have other set of magnets, and by trying to pull it together, so since it's not actually attracting each other, I know that also this is a North Pole now. Okay, so as we say, we need 2 North Poles on each end of the battery. So therefore we're gonna get this side of the battery, okay? And this is a North Pole, and then this will be a North Pole also. So that is basically the setup. Then as you will see, only thing you have to do now is to place this setup into the solenoid that you just created and let the magic begins.
Qué reguero. Una paradita.